Good morning, everyone. Thank you so much for joining the live webinar with TCS and ARC on AI and digital twins. This is Raj, your moderator for the day, and I'll walk you through the agenda we have for today. Thank you once again for joining us. A quick overview or an introduction before we get started. Thermal power plants today are facing a lot of challenges, and I'm sure most of you are aware of it. Today, we are thinking about a future where, if we can imagine operating our power plants at highest efficiencies, irrespective of varying operational constraints. This is the ideal future which we are working towards, and in that, we would want to understand the challenges which we'll be facing and how to mitigate those challenges. That is where we have two eminent speakers today with us to talk about the market conditions, the challenges, and what is required, and the ways to address these challenges. So if we were to achieve this, we will be moving from a condition where we make trade-offs between cost, climate, performance, to harnessing abundance using the wealth of data that you will already be possessing in your power plants. Allow me to introduce our presenters for the day. First up, we have Harry Forbes. Harry Forbes is the Research Director with ARC Advisory Group. He has over 30 years of experience in automation, power generation, modeling, simulation and control, and optimization. He has written prolifically for leading publications like Power Magazine, Hydrocarbon Processing Magazine, and as well for many technical and industry conferences. Also, interestingly, in his rich career, he has also had hands-on experience working on a performance and automation engineer in fossil and nuclear power generation. A warm welcome to you, Harry, today. So Harry is going to be talking about two very interesting things. First up, he'll be talking about how US fossil power plants are challenged today because of the market conditions. And subsequently, he has a word of advice for us and also a word of caution on what are the metrics that fossil fuel power plant operators should be concerned about. Next up, we'll be having Ajay. Ajay Singh is Senior Director with Tata Consultancy Services, and he's heading IoT power generation and utilities practice for North America and LATAM. Ajay, in his rich experience spanning over 24 years in power generation, utilities, and transportation with GE and Rolls-Royce. His expertise lies in engineering, advanced control systems, and autonomous operations. Welcome to you as well, Ajay. So Ajay today will be talking about a very interesting solution, TCS Intelligent Power Plant Solution. So he'll walk you through the solution, talk about the use cases for GTCC. He'll also be giving case histories and the benefits, and we'll be taking question and answers. With this, we'll get started with the presentation. I'd like to hand it over to Harry, and I kindly request all the participants to actively participate and share your questions in the questions tab. Over to you, Harry.
Thank you very much, Raj. This is Harry Forbes. I am going to talk about the challenges that are facing fossil power plants in the United States. There's some significant changes that are coming in the market that will impact the operations of plants, and I want to talk about these. So let me make 2 points, really, and I'll cover 2 points here. First is that the changing market conditions in the United States are going to have a big impact on the operations of all years. And this is not just coal, but combined cycle, a gas-fired combined cycle as well. These operational changes will have to be supported without new staff, and they will change the performance metrics as well, and will increase the need for digitalization as an aid to operations and maintenance. So let's begin by looking at what is driving these changing market conditions. The U.S. power system operates in a number of different markets, each with its own market rules. Customer load growth has been flat or negative in most of these regions since the time of the financial crisis. During the same period, renewable generation capacity, that is solar photovoltaic or solar PV and wind, has increased dramatically. but this type of renewable generation is not dispatchable and generally operates with a lower capacity factor than fossil-fired units. The general trend is for bulk power prices in the United States to reflect the cost of generation using natural gas. The price of natural gas has been falling and remains low. The chart on the left of this slide illustrates an 8-year trend of average bulk power prices in 2 major markets in the United States in dollars per megawatt hour. This is the ERCOT market in Texas and the PJM market in the Middle Atlantic states. The 8-year trend is also plotted of the average Henry Hub natural gas price in dollars per million BTU. This is a benchmark natural gas price in the United States. Gas prices in the U.S. are being held low by the availability of large amounts of non-conventional or shale gas. And U.S. export gas capacity has been built and may change over time, but is not likely, in our opinion, to change the overall gas price very much in the foreseeable future. So as a result, look at the chart on the right, which shows the distribution of hourly power prices during a recent year, 2017, in another market area of the United States, the New England states. Now, there is roughly a little more than 8,700 hours in a year. Power prices were higher than $50 a megawatt hour for only about 10% of that time. Almost all of the remainder hours to $40 per megawatt hour range with a median price of about $25. So these low power prices, $20 to $40, are the range that can be expected in the U.S. for some time to come. Along with continued growth in renewable generation capacity and flat overall customer load growth. The next slide illustrates the changing mix of electric generation capacity in the United States. The positive region on this chart shows the additional new generating capacity added each year by type. The negative region shows the retired generation capacity, again, by type. Capacity additions are mainly solar PV, which is shown in yellow, natural gas combined cycle, which is shown in blue, and wind, which is shown in green. Capacity retirements are primarily coal, which is shown in black, and simple cycle gas turbines, also shown in blue, and some nuclear, which is shown in brown. What you can take away from this chart is that over time, the mix of available generation capacity becomes less and less dispatchable as renewables make a greater and greater portion of the available generating capacity. So what is the impact of this change on the overall fossil generating fleet? Let's take a look at that on the next slide. This is a forecast from the Department of Energy of generating capacity utilization. In the utility industry, we call that capacity factor. It's a forecast of capacity factor by type of unit. Now note that coal capacity utilization rises over time, probably due to the retirement of some older coal units, but still remains about 70% in the long term. And this is low by historical standards. A base load coal unit would target a capacity factor in the range of 85 to 95%. For combined cycle, which is shown in tan, capacity factor has been rising for about 10 years, but starting now it begins to fall steadily. The existing fleet of gas-fired combined cycle units will be used less and less going forward. So both major types of fossil units, coal and combined cycle, can expect to be operating at lower capacity factors with the long-term impact being greater on the gas-fired combined cycle units. So what is the impact of this on the operation and maintenance of these plants? And that really takes us to my second point, that the reduced capacity utilization will bring some major changes to operation. Let's look at that now. For operations, plants are going to see much different operating modes than they are accustomed to. First of all, we'll see more partial load operation, which is very challenging for coal plants and less efficient generally for gas-fired combined cycle units. We'll see more cyclic operations. Units that cycle perhaps once a week can anticipate that they will eventually be cycling 5 to 10 times per week, and this is a huge increase in the amount of cycles these units have to go through. These units will also be required to ramp up and ramp down on a schedule and may be called on to follow load and reverse ramp at times. And there will be many more unit starts and shutdowns, many from both hot and cold conditions. The key operational metrics are going to change. Emissions is always a key metric, but it will be much more difficult given the far less steady state operation. Turndown ratio of a plant or unit will become more important to support stable partial load operation. And ramp rate will become important to follow dispatch schedules without overstressing equipment. Equipment temperature differentials and mechanical stresses are far more important in these kinds of dynamic cyclic operations than they are in steady state operation. In terms of maintenance, key metrics will shift to failures that can result from this more cyclic operation. These include differential temperatures and the resultant mechanical stresses on equipment, such as boiler and HRSG tube failures and stresses to rotating equipment, especially turbines. Sustained operation in these highly cyclical modes without any additional staff is leading many utilities and IPPs to consider digitalization and especially digital twins as a more modern way to monitor and to diagnose and to optimize these generating units in these more challenging conditions. Digitalization and the development of digital twins have become much more feasible and popular in many industries, including the electric power industry. But to be successfully integrated into power plant operations, you need more than just digital models of your equipment. So now I'd like to talk about some of the requirements for digitalization of power plants and power plant equipment. What plant operation and maintenance staff really need is this. They need real-time insight into the impact of cyclic and dynamic plant operations on the plant performance and on the mechanical equipment. Now, I point out that any digitalization solution will be required to work for the long term. Remember that the changes to operations and the changes to the markets are a long-term situation. So the digitalization solution needs to work for a long term. So in ARC's opinion, it is most important that the solution be maintainable over time, which means that it should be part of a comprehensive services offering that includes expertise in engineering, in operations, and provides continuous support services to the utility or the IPP. You will need to integrate dynamic models of your plant equipment into the solution, and the solution will need to give you real-time visibility of key metrics. It should provide intelligent guidance for operations and plant optimization, and it should include an integrated analytics capability so that it supports operations. Now, many utilities have some experience with this kind of capability that was begun 15 or 20 years ago in utilities. What they found from operating these kind of applications decades ago was that what was lacking was not so much the models as the analytics. There is a big difference in a plant between a single transmitter failure and overstressing mechanical equipment. And it's the differentiating between these conditions is the responsibility of the analytics within the solution. In summary, I'd say that the major challenges to digitalization are accurate plant and equipment models that can be maintained over the long term, the intelligence supported by diagnostics and analytics, to identify failures and distinguish between serious and minor issues. Finally, understand that this solution should be useful to both operations and maintenance organizations, and it should help these areas to collaborate. So let me summarize the main points that I have presented here. First, the existing fleet of fossil power plants in the U.S., both coal and combined cycle, face lower capacity factors in the long term. This will mean more unit cycling, perhaps much more for some units, and more partial load operation and load following. Second, these new modes of operation will change your key metrics with even more focus on dynamic response and the impact of dynamics and partial load operation on your plant equipment. Third, solutions for digitalization need to be designed for a long life. So they need to be maintainable, and they need to have a strong analytics or AI component in order to provide accurate and valuable diagnostic information. And the results provided by digitalization solutions should provide input both to operations and maintenance organizations within the plant. With that, now I'll turn the floor over to Mr. Ajay Singh of Tata Consultancy Services, TCS. Ajay will discuss the TCS Intelligent Plant 2, or IP2. TCS IP2 is an intelligent digital power plant solution leveraging a number of technologies, including digital twin, to optimize the performance of power plants. Take the floor.
Thank you, Harry. It was a good summary of current trends in the market and challenges that our power producers are facing. So good morning, good afternoon, and good evening, everyone. And I thank you all for joining. I know it's late at some parts of the world. So is there a solution that can eliminate silos across the organizations and generate revenue for the businesses at the same time? Well, let me talk about this intelligent power plant solution, IP2. Today, I'm going to show you how this field-deployed solution has helped our customers increase productivity, efficiency, avoid equipment failure, and optimize cost. Here's how I'm going to do it. In the next few slides, my goal is to share some details on the IP2 solution and how it fits into the IT/OT landscape, and then go over 5 case histories that we have deployed in existing power plants across the globe. According to Gartner's 2019 report on top 10 trends driving the utilities, we are at the beginning of another AI revolution. The number of enterprises across all industries implementing AI grew by 270% in the past 4 years. So in the next slide, let me talk about IP2. TCS IP2 provides an intelligent digital infrastructure that leverages AI, digital twin, and IoT technologies to optimize performance of the thermal power plants operating at partial and full load conditions within the constraints of the existing equipment and systems. This IP2 offers real-time insights captured from assets like turbines, HRSG boilers, generators, and balance of plant using sensor input from the control systems. So the 4 building blocks for IP2 are, the first one is the digital twin as the fundamental building block. What is it? A true digital twin is a virtual counterpart of a real asset, which enables other software, systems, and operators to interact with it directly, bypassing the real asset. All digital twins must include a model of the asset, data from the asset, a unique one-to-one correspondence to the asset, and the ability to monitor the asset. So in our solution, what we do is we create a digital twin of the plant, a digital twin of the processes, and a digital twin of the assets. The second aspect is we combine plant domain knowledge and engineering analytics to generate useful insights. The third pillar is we integrate operation and maintenance data. And this is the key differentiator for our solution because this combination provides unique insights for the users and allows us to eliminate silos within the organizations. And the last one is we use IoT architecture as the fundamental block. but the solution can be deployed either on-premise or hosted in the cloud. So let me talk about the key features of this solution. First one is a reporting dashboard. Provides a dynamic real-time view of the important parameters. Artificial intelligence-based operational assistance for off-design operation points, that is base load, partial load, steady state, and in-transient state. Asset predictive and preventive maintenance, which preempts equipment damage to prevent catastrophic failures. Also allows us to conduct failure analysis, which adopts FMEA and based models to diagnose and predict plant issues. And the last one is digital worker enablement, which uses augmented reality and virtual reality to help personnel access and capture system information in an immersive, interactive manner. So on the right-hand side, what I've shared is some examples of value delivered to our customers. And later in the presentation, I'll be sharing the case histories in detail. So next, let me provide a bit more insight into the IP2 functionalities. The IP2 solution has 4 key functionalities: process twin, asset twin, digital worker, and plant twin. So what is a process twin? We create a twin for each of the key processes, and for each sub-process, we're able to monitor the performance of the process as well as the KPIs. We also have failure mode and effect analysis, FMEA is incorporated. That is, if there is a problem in the process, that is, if a KPI is not where it is as desired, then we have the ability to identify it. It also allows us to optimize the system at that level, and the solution suggests new set points which can be used to change the setting so the process comes back to the normal level. Similarly, we create an asset twin to monitor the KPI, etc. And under the digital worker, we want the operator to be mobile and ensure all key KPIs are available to them on mobile devices so they have access to the required information. In addition to that, we also automate all the manual processes for them. So by combining the process twin, asset twin, elements, and the digital worker, we derive a plant twin. So what is a plant twin? With this, we provide the ability to monitor the performance of the plant, key KPIs, and have the functionality to drill through detailed analysis. For example, if there is an issue with the heat rate, we can troubleshoot it, find out where the problem is, and then find anomaly at that plant level and resolve it. So next, let me take you through the high-level architecture. As we can see at the bottom, we have the equipment, example, boiler, steam turbine, gas turbine, generator, etc. These are all connected to the control system, which is DCS, PLCs. And then above that, we have the enterprise layer, example, the Histories, SCADA systems, vibration, flame sensing, etc. And this is a typical setup in a power plant. So what we do is we create a data lake, which connects all the data from operating systems as well as the enterprise systems. And then these converge into a data lake, and then we create the IP2 solution above it. So in summary, IP2 adds to the existing systems, leveraging data from all diverse sources and helps derive actionable insights. In the next slide, let me go over the digital twin. So how does self-learning AI/ML enable optimization with digital twins of assets and processes work? Let me describe the process related to build these modules. In the bottom half, we highlight the TCS IP2 data processing, prediction, and optimization modules. So first thing we do is we select the manipulated variables such as the IGV angle. Next, we identify disturbance variables and constraints. So for example, load, metal temperature, etc. And then lastly, we select the plant process variables such as NOx. So the type of data we use to build the digital twin is both a steady state as well as plant test data. Next, we use multiple algorithms, perform sensitivity checks, and then tune the model to validate it. And these models are self-learning. So in the top portion of the slide, it's a little bit of a process discussion. We're highlighting the process where IP2 Solution suggests the set points, and the operator selects those in the plant control system. And then the values from the plant process variables are compared with the predicted outputs from the IP2 module, and based on those, alerts and alarms are generated. So next, let me go over the typical use cases that we have covered. Here, I would like to highlight typical use cases that we have addressed in the gas turbine combined cycle plants, but will not go through each one of them as I want to get to the turbine optimization and diagnostics related use cases have been worked on. So for example, HP, LP, IP, performance monitoring and diagnostics. Similarly, we have use cases that we have addressed for HRSG optimization and diagnostics. Some examples are aux power consumption optimization, gas turbine exhaust gas temperature optimization. Similarly, we also have condenser optimization use cases. An example under that would be cooling tower optimization. And then we have use cases that we've addressed for feed water heater optimization and diagnostics. So now comes the important part, the case histories. In the next 5 slides, what I'll do is I'll be taking you through examples of field deployed solutions. 2 of them are case histories related to gas turbine combined cycle plants, and then 3 of them are case histories related to coal-fired power plants. So the first case I would like to share details on is related to gas turbine failure prediction. This has been deployed at a 400 megawatt power plant in Japan. So this is how it goes. A Japanese customer was very desperate. They were getting huge number of service requirements from their gas turbine customers, and were so frustrated with lost revenue, productivity, and unplanned outages that they launched a contest where they announced that they will share their data and invite several partners who can help them get out of this desperate situation. So the goal was to be able to detect anomalies beforehand to avoid failures and plant shutdowns resulting in plant downtime. Several partners participated in this contest. Our team analyzed almost 3 years of historical data from almost 300 operational parameters, applied artificial intelligence and machine learning techniques to develop data-driven models. And these models were with as much as 97% accuracy. And then we developed fault prediction models, and then we also won the contest. So our solution provided the OEM the ability to analyze the fault signatures proactively and predict the failures 2 to 3 hours before the actual failure, and reduced unplanned downtime significantly, and that delivered savings of as much as $250K per shutdown. So the key differentiator for the customer was our approach, because we kept them engaged throughout the journey. Let me go to the next one. The second case I would like to share is related to this HRSG system optimization. This has been piloted at a 300 megawatt combined cycle gas power plant in Mexico. So the story here is that there is a power plant located south of Arizona border in Mexico, and traditionally they used to run at base load, but due to addition of renewable generation sources in the area, this plant will be cycling more than it has been in the past. So in this plant, there is a gas turbine, a reheater water tube HRSG, a steam-cooled combustor. And the goal here was to reduce problem of FAC, corrosion, thermal fatigue, O2 pitting, and HRSG due to partial load and cyclic operation, as well as poor water and steam chemistry. So to minimize the customer's pain, we took years of data and did 2 things. One, using our domain knowledge, simplified it and built optimization models and ran against with the current data to validate it. And the second thing we did was, in addition to the optimization model, we created a detailed FMEA to bridge the knowledge gap with the newer plant operation personnel. And this was above and beyond the ask. In the end, we were able to demonstrate to the customer that optimization of water and steam chemistry, superheater attenuation, and corrosion monitoring was possible, as we were able to successfully replicate the past incidents. The process FMEA for HRSG system was useful in tracing anomalies much faster compared to the existing manual process. And above all, the folks didn't have to go through the multiple documents while troubleshooting, as the FMEA linked both operations and maintenance aspect of the plant. Now I'll share the case histories related to coal-fired power plants. The third case I would like to share details on is related to fuel gas exit temperature system optimization. And this has been deployed at a 2 by 525 megawatt coal-fired power plant. So the story here is that fuel is as much as 60% of the operating cost for power plants in India. This is something we all struggle where we have to find ways to save money. Any deviation in the heat rate results in a situation where money is left on the table. So the customer wanted the ability to optimize the plant in abnormal scenarios such as coal blending, partial load operation, resulting in tube failures and losses and all that. So using AI/ML techniques and the past data, our team developed a digital twin that was able to suggest burner tilt angle, optimum setting for the coal flow, damper position, etc. And this resulted in a saving of as much as $700,000 to $1 million. Let me go to the next one. The fourth case I would like to share details is related to a 2 by 1,000 megawatt coal-fired power plant in Japan. The arrangement at this plant is that it's a tangential coal-fired power plant, and they have blended Australian coal with biomass. So the story here is that the power plants running in Japan already run efficiently. However, with the rising emission norms for the coal-fired power plants, the customer was facing huge pressure to reduce the emissions and reduce the operational costs at the same time. In order to address this problem, we built a digital twin which gives advice for the best setting of the input parameters. And this was done for combination of two types of coal and biomass. And the digital twin was purely data-based. Because in the past we've used physics-based models, but we have the ability to derive purely data-driven models, as much as 95 to 97% accuracy. So the TCS data scientists, along with our domain experts and plant engineers, worked on almost 500 sensor tags with more than 3 years of data, and we created almost 61 models, which went into the digital twin. And that has the capability to recommend the optimum settings for the input parameters to the operators. So as the customer started to use the recommended settings, it resulted in 10% of NOx level maintaining other critical parameters and within the range, and it reduced operation cost by almost 2%, which equates to almost $3 million annually. Let me go to the last one. The fifth and final case I would like to share is also related to a 2 by 1,000 megawatt coal-fired power plant in Japan. And this is a case related to flue gas desulfurization system optimization. So the question is, in a given power plant, what are some of the other things we can do to save dollars for the customers so they remain competitive? Let me share. The flue gas desulfurization is a system that removes sulfur content from the flue gas, thereby helps complying to the rising emission standards. So flue gas desulfurization plays a crucial role in thermal power plants, but at the same time, a lot of cost is involved in its operation. Limestone is consumed in the system for carrying out the chemical reaction to remove sulfur dioxide, and multiple recirculation pumps are operated to circulate the limestone slurry throughout the system. So as you can see, the system is pretty complex. And it's also difficult for the operator to carry out this process by himself in an optimized manner with optimum consumption of limestone and the operation of optimum number of pumps with reduced SOx levels at the output. So the goal in this case history was to optimize operation cost. To help the customer, first we conducted a process analysis and identified the system parameters, and then implemented a digital twin of the FGD to optimize the operation of the system. As a result of this solution, the customer was able to project in advance that the limestone consumption will reduce and overall electricity consumption for the operation of the pumps will also be reduced, thereby saving dollars. So to summarize, we can see from these case histories that we're able to solve different type of customer challenges and that it helps optimize cost, increase efficiency, availability, and flexibility, as well as decrease emissions. So the question is, how does it translate into real dollars? The potential benefit, let's say if we assume a 1,000 megawatt plant on a very conservative basis on an annual basis, if we gain 0.5% to 1% in efficiency, it equates anywhere from $700,000 to $1.5 million. Similarly, if we gain, let's say 1 to 2% in NOx power consumption, it's a savings anywhere from $1 to $2 million. If we're able to increase the availability factor by, let's say, 100 to 300 basis points, it equates anywhere from $1 to $3 million. And finally, if we're able to save, let's say, 2 to 3% in operation and maintenance cost, depending on the power plant make and complexity, it's anywhere savings of $700,000 to $1 million. So to sum up, it's a potential savings of anywhere from $4 to $10 million per gigawatt annually. Next, I think we'll transition into the Q&A section. So Raj Bharat, please feel free to take over.
Thank you so much, Ajay. I'm sure that was a very interesting presentation for all of us. At this moment, something comes to my mind. This is a famous remark which a corporate leader made in India. So this is how it goes. He said, "In God we trust. Others, please bring data to the table." So after the presentation, we sort of appreciated where we can harness the power of data to get very valuable insights. I'm sure our audience was also equally enthused, and I can see that in the flurry of questions. So I'm going to call out the questions. No preferences here, even if I wanted to, because I do not see the names against the questions. So a couple of questions here, Ajay. I'll start with you. So this is how it goes. What are the typical timelines for implementing such a project? To build the models and to tune them. Over to you, Ajay.
Yeah, so the answer is it depends. We have been able to use, small use cases and be able to do the projects as fast as in 3 months to 4 months. And if it's a complex set of use cases, then it's anywhere from, I would say, 3 to 6 months to 8 months. Really depends on the make of the power plant and the use cases we are addressing. But that's the timeline, at least to get the initial, I would say, engagement started.
Sure, Ajay. Thank you for that. The next question is to Harry. Harry, the question goes like this. Why would unit cycling change so much because of a relatively small change in capacity factor? How is that possible?
Well, the difference is whether a plant has to cycle on a daily basis or a weekly basis primarily, and with the different availabilities of renewables. So if a plant becomes daily cycling, it can go from 1 cycle per week to 5 cycles per week, say. Also, the volatility, if you will, of renewables for wind or solar, they can change their output very quickly, and that can add cycles to a unit as well. So even small capacity factor utilization changes can have a very big impact on the cycling of units.
Interesting. Thanks for that, Harry. Let me try to get one more question. I'll try to get a question for Ajay. I'm just searching through it. This one seems interesting. Ajay, this is how it goes. So what is the first step, or what type of data is required to get everything started?
The easiest way to get started is we obviously need operations and maintenance data, and from the PI historian, or depending on what the customer has. But we can take data which is a few months long or as much as a few years. So depending on what's available, we can use that and get the process started. The more data we have and better quality data we have, the better results we can derive. But using our domain expertise, we have been able to help the customers, in these areas as well, where if the data is not as clean as it needs to be, we can help out and, develop the models and whatnot. But operations and maintenance data is the key.
Absolutely. I think I have one more question for you, Ajay. So they're asking if we have closed loop control, and how do we make sure that the set points or the recommendations that's suggested by the model are valid and they can trust them?
So as most people on this call would, have a lot of experience with power plants, the one thing we don't want to do is give the control in the hands of the machine. And we do that by building the, balance, the safeguards into the model and limits, which kind of doesn't allow the numbers to go haywire. And then as far as closing the loop, we have the ability to help customers do that. But so far, most of the engagements have been where we have suggested set points and the operations people have decided, how to run the power plants. But the key is, validating the model thoroughly and then checking it with the real-time data, and then also building the safeguards into the model.
Got that. Thanks for that, Ajay. Harry, I think this question is for you. This is what the question is. Why do you place so much emphasis on model maintenance and diagnostics?
This kind of comes from experience that utilities have had. Utilities generally have been able to build models, but they've had much more problems maintaining models over time. So maintenance is something that, in general, utility staffs don't have time or the expertise to do. So they really need to have a solution that guarantees their model can be maintained over time. And as far as diagnostics goes, as I mentioned in the presentation, I think the analytics, the AI, whatever tools are employed, really need to be able to distinguish common single failures. For instance, a lot of in experience of using these kind of models, utilities have found that roughly 4/5 of the situations that are identified as anomalies are caused by things like sensor failures. And so the analytics needs to be able to distinguish between be that important and something like a analysis that shows rotating equipment as being overstressed. So the common garden variety anomaly is probably caused by a sensor failure, and it's not necessarily that important. It's an issue that needs to be addressed by maintenance quickly, but it doesn't threaten equipment performance or capital equipment. So these kind of responses need to be integrated into the operation and maintenance procedures that the staff uses for maintaining the equipment.
Got it. Thanks for that, Hari. So here's another question, which is somewhat in the same realm. Ajay, this is to you. I'm just phrasing it here. Does your model work in all plant operating scenarios? And how do you say so?
We make the model work in steady state, part load, and then the transient is depending on data available, but we're not able to, commit to that unless the data quality is good. But mostly we are able to satisfy, with the use cases that I shared, right, during the presentation, that steady state part load, steady state base load, and then lower loads of operation as well as the units are being cycled. So I hope that answers the question properly, but it also depends on the quality of the data that we have, and then the challenges that the customers are facing.
Thank you, Ajay. I get that. So we are in this is an interesting question. So we are in the era of renewables. So one of the viewers have asked, how is IP2 applicable in a renewable landscape?
Is that to me, Raj Bharat, or Harry?
That's
right, Harry to take it?
Yeah, Ajay.
So, I'll go ahead and take it. So in the renewables, the artificial intelligence and machine learning is applicable to renewable systems as well, where we want to monitor the wind farm behavior and whatnot, the asset management strategy, as well as the asset itself. So we definitely have solutions that can help the customers. We didn't use renewables use cases here, but certainly IP2 has the ability to help out the renewables customers as well. And it's very applicable to the use cases in the renewables.
Thank you, Ajay, for that. So, this sort of, let me also try to take a question here. So one of the questions says, how have you been able to get this kind of results with the data analysis that you've done? I mean, some of the viewers have sort of commented the results we've achieved. So drawing from what Ajay had spoken, this is primarily because our approach is data-based, where we will be taking the historic data, build digital twins out of it, which way it becomes a true reflection of the assets. And the solution is also modular. In that sense, any existing models that customers would have would also be taken into consideration. That way, it's a holistic twin, digital twin, which is a true reflection of the assets and processes. Probably that answers the question on how we have been able to achieve these results.
Yeah, one comment I'll add to your answer, Raj Bharat, is that we are also platform agnostic. We can build the solution pretty much on any platform if a customer has already invested in. So I just wanted to add that.
Absolutely, Ajay. Platform agnostic, and it can also be hosted on-premise. So that raises an interest that actually relates to one of the questions asked by a customer, if it can be hosted on-premise. The answer is yes. We have deployed it on-premise in quite a few power plants, and it can also be hosted on cloud, depending on the interest that the client has. And if it is hosted on cloud, it will be scalable, and with a single instance of the solution, we'll be able to cater to multiple units of the power plant, and you can have a holistic view. That sort of sums up the presentation that we had for today. I urge our audience to shoot any questions if they were unanswered to our contacts, which is displayed in your screen. Please feel free to address Ajay or Harry right ahead, and we'll be very glad to take your questions and take this discussion forward. With this, we will be drawing a close to this webinar, but quickly before that, let me also tell you how you can access it at a later point in time. This webinar recording will be available on demand on the platform, and it will be accessible through the same link which you used to register to this webinar. So please feel free to access the link and get hold of the recording in future. So with 9 minutes to spare, we give you some time which you can take for yourself. And thank you so much for joining the webinar, and we'll be very glad to host you again shortly. Feel free to write to Ajay or Harry. Until then, thank you so much for joining, and have a good day. Bye-bye.